Okay.
Good afternoon. My name is Marcos Pereira. I come from Brazil. I'm with the Catholic University in Rio de Janeiro. Thanks for attending my talk. And I will present you some results, initial results of my PhD student, Ms. Roberta, which works with multiaxial high cycle fatigue criteria, a lot of 6 criteria, different criteria, to know about the efficiency of design project of these crankshafts. So Brazil is a large country. We have about 2,010 million people. We are divided in 26 states and 1 more federal district. And here we have our energy scenario, our energy share. We have most our energy comes from water, hydro water plants, but also have about 20% from power plants which works with fossil combustibles. And here we have a scenario of the installed thermoelectric fossil plants in Brazil. We can take a look that most they are at the north of the country, because here we have so flat rivers, so the hydraulic is not so easy to become here. And here, from the middle of Brazil to the south of Brazil, we have the hydraulic power plants working with that. So, thermoelectric fossil is about 20% of that energy that we need. We are doing that. But they use normally diesel or gas engines. And as they are combustion engines, they work with pistons, cylinders, and also with crankshafts. But the crankshafts are huge crankshafts. They are about 3.5 tons, about 4 tons, and it's a complex loading. And the problem is that when it breaks, when you have a failure in the crankshafts, you don't have only problem to replace that, because it's an engineering situation to replace sometimes the crankshaft inside of the engine, because you have take out of the roof of the room to open the engine and to replace here inside the crankshaft. But sometimes the problem is that is also the blackout that you have in all regions, depending of the demanding of these power plants. So I suppose that when you are working or talking about crankshaft design, fatigue resistance, complex loading, structural integrity, extension in reliability, durability, and performance in service life are normal keywords for that. It's very, very easy to think that they are always, the designers think about that to do the correct design of the crankshaft. But the problem is that crankshafts are complex geometry. You have thermal loads working with that. Sometimes you have a hydrogen enrichment together with, and you have a fire sequence that is not very easy to understand how the things are going. In the sequence of the pistons, they are not as normal motors, outcast motors, they are not exploding in sequence. And the stresses, the foamis stresses, or the shear stress, or the normal stresses that comes inside of that is very complex to achieve the real what's going on. Okay, the people think about design criteria, but they failed. And we can see a lot of crankshafts with cracks around that stops to work, and you have a lot of expend money to recharge that, or to replace that in the right place. So, when you're talking about fatigue loading, multiaxial is very complex, and normally the criteria is to divide the space in 2 situations. What you say, the left hand or the right hand of the model, which means the safe situation and the unsafe situation. The fatigue criteria is expressed like inequality from one hand to the other hand. We have many decades of research, a large numbers of research of models is presented with that, but they are always criteria of failure is stresses against fatigue resistance. So the motivation of this work is a long-term project involving thermoelectric power plants in Brazil that I'm engaged with that. And this presentation is based on applicability of 6 models, 6 different models for the design criteria for crankshafts. Mataki, McDiarmid, Findlay, the most famous one, Carpentieri Spagnoli. Professor Carpentieri should be the chairman of this section, unfortunately he's not there. Lou and Mahadeva, and also Papadopoulos. So the whole of the work, the things of the work is to compare different models to think how it's coming up with this comparison. So we have here, each model has the own constitutive laws, like Mataki, McDiarmid, Findlay, Carpentieri Spagnoli, Louis Mahadevan, and Papadopoulos. And what's going on in these models is that you have the left hand against the right hand. It means loading condition against fracture resistance, fatigue resistance of the materials. It's the main approach to do in this design. We're working with multiaxial fatigue. So they are here always in full reverse loads. We have also properties with that. And we have also in these constitutive laws some materials constant. Defined here what is going on. One of the criteria, Papadopoulos, it's only necessary to identification the applied stress amplitudes. It means the normal stress amplitude and also the shared stress amplitudes. We suppose that could be the easier to apply for the design. But the 5 others, Mataki, McDiarmid, Findlay, Spagnoli, and Carpentieri, Louis Mahadevan, we need to find a critical plane. Critical plane is the plane where the fatigue damage can occur, leading to a crack nucleation, and then after that is starting in the critical plane, it turns up, it moves to the fracture plane of the material. So here we have a design for the normal stress amplitude acting in arbitrary plane, defined by this angle here, the psi angle, and Mataki and McDiarmid, they have their own possibility to achieve the critical plane. Findlay has another possibility to find the critical plane, as well as Carpentieri Spagnoli and Louis Mahadevan also. They are distinguished, or they have distinguished criteria to find the fracture plane, and from the fracture plane we can achieve the critical plane. It's more work on it to use Carpentieri Spagnoli and as well as Lou and Mahadevan, because the previous work we can see Mataki and Findlay, we needed to find the fracture plane, but only the critical plane direct from the expressions. So they are distinguished also with the criteria from delta here, what means the delta, both, but we can compare here, taking into account the fatigue resistance of the material, the intorsion again, the fatigue resistance in bending. We can see that this delta that both of them need to choose, they are fast the same. There is no apparent difference between both. So what was the methodology? Use these 6 models. After that, experimental loading database from literature, full reverse synodal in phase bending, metallic materials with different fatigue behavior, load conditions correspond to the fatigue limits, and the fatigue life extends over 10 to 6, 10 to 7 numbers of failure. It was the criteria that used with that. We use also 7 different materials with different hardness and different age and different ultimate stress, different fatigue resistance in bending and different fatigue resistance in torsion, to things how applicable are the models with different materials, dueling with the hardness of the materials. And here we have the results. Here is the fracture plane of the materials, very easy to calculate for each one. And here we have the fracture plane, and here we have the critical plane according to Mataki, McDiarmid, Findlay, Spagnoli, Carpentieri, and also Louis Mahadeva. So we can see that there is different conclusions from this table. Mataki and McDiarmid possess the same critical plane, here in red. Carpentieri, Spagnoli, Louis Mahadeva, and Findlay partially indicate critical planes which are close to each other. But Findlay model depends on the material. Sometimes Findlay works like Mataki and McDiarmid, but sometimes Findlay is very different from, sometimes Findlay is very, very comfortable with Carpentieri Spagnoli or Louis Mahadeva, but sometimes Findlay is very in a good agreement with Mataki and McDiarmid. So it's not very, very definite what is the model of Findlay here, although Findlay is large used to do the design criteria of the crankshafts. And also here we have what's going on with another kind, 3 types of materials, 3 different materials. And also we see that Mataki and McDiarmid models possess the same critical plane, and the Carpentieri and Spagnoli, except for the cast iron here. And Louis Mahadeva and Findlay partially indicates the critical plane with orientation that is close to each other. So we can also see a variation of the fracture orientation with the ratio for the applied stresses. And when the higher is this ratio between the applied stresses, the lower is the fracture plane, and also that the fracture plane tends to 0 for uniaxial normal stresses up to 40 and 5 degrees for poor shear loading. And also we can, in this graphic here, see the variation of the critical plane with the Mataki and McDiarmid. We see that they are very in good agreement. The variation with that will also increasing the stress applied for the materials. So the last but not the least commenter that I would like to do, there is error index. Error index is a possibility to know how adjust is the model that you are using, no? And we can see that the error adjusting is about -10 to +10%, and is exactly the left hand against the right hand of the model. It means how far from the fracture is the component. We can see that without the McDiarmid, everyone said that the crankshaft will not fail. We can see that some are more conservative than others. For instance, Louis Mahadeva and also Spagnoli Carpentieri is not so conservative as Mataki, as Findlay, as Mataki, Findlay, and as the last one. And so I can give my conclusions up to you. The working is still going on. We are doing now a financial element analysis to know exactly the states that are acting the crankshaft, calculation of fatigue life for steels adopt, making use of models in these questions, making use of another criteria, for instance, fomisis, old one but very, very good, and biaxial fatigue tests to promote the model's efficiency in predicting fatigue life of the crankshaft. Thanks for attention.
Thank you. Thank you very much, Marcos, for nice presentation.